Hey there! Welcome to the first tutorial on portfolio allocation using Python. Before we're able to conduct any sort of analysis, we're in need of pricing data for selected financial assets. In this video, I will demonstrate a very efficient and dynamic way to extract pricing data from the web. Let's just dive straight into it. First things first, we need to import the modules. We'll need to import pandas as PD, as we'll be working with panel data, which in turn explains the abbreviation PD. Furthermore, we need to import the numerical library, NumPy, as MP. NumPy essentially allows for very fast data generation and handling by utilizing arrays, and at the same time it allows us to do some basic linear algebra as well later on in the series. Furthermore, we will need to import the pandas data reader function as web, which we'll be using to extract pricing data from the web. And then, as we'll be working with time series data, we have to import datetime as DT. Additionally, from matplotlib, we import pyplot as plt, since we're going to generate some graphs in the videos to come. And finally, we import pickle, which allows us to efficiently serialize objects so they can be saved to a file and loaded in a program again later on in a very efficient manner. Next up, we need to specify the assets which will form our portfolio. To keep things simple, I selected 3 exchange traded funds. So let's create a list over here. I selected GUFT, SPY, and CEY, which are tickers of 3 exchange traded funds. GUFT is an ETF that tracks the performance of a large government bond portfolio. SPY, an ETF that tracks the S&P 500 index. And finally, CEY is an ETF that tracks all emerging markets. You are, of course, free to fill in any ticker of a financial asset you desire, conditional upon the fact that it is an accessible ticker in the source we're using. Then we need to establish our estimation period. The estimation period is essentially the period over which we will extract our prices and calculate our mean, returns, and variances, which are all to be extrapolated into the future. Our start date will be the 1st of January 2017. So we say DT datetime 2017 11, and our end date will be, let's say, today. Okay, now it's all set. Let's define our returns function. First, we need to create an empty panel data frame, which we will fill up with price data from our selected assets. So we say price is equal to PD data frame. Since we have to extract price data from each ticker in our tickers list, we need a for loop. So we get for ticker in tickers, and this tickers, of course, refers to the list over here. So we'll essentially iterate over the items in this ticker list. To actually extract the pricing data of each ticker in the ticker list, we use a data reader function. So we say df is equal to web data reader. This data reader function, you feed it an official ticker name, a source, a start, and an end date. In our case, the ticker is already specified. It's the ticker. The source, we select IAX in this case. And the start and end date are also already specified. After specifying the parameters, it provides you with the price data of the specified ticker. So in this case, it will select each being iterated ticker and create a data frame for that specific ticker. Then we need to make sure that the extracted data is in panel data format. So we say df is equal to PD data frame df. Now, if we want to print the data, we essentially say print df, and we run our function. Okay, so this looks promising. We essentially have 3 individual data frames now for each ticker, which all have an open, high, low, and close, and a volume column. In essence, we're only interested in the close column of each data frame. So we say data frame is equal to df, and then we only select the close column. By extracting only the close column of each data frame, we essentially, it leaves us with a single series. Next, we can rename the column to the respective ticker names. That is, we replace the string close with a string equal to the ticker name. To do so, we can say df columns is equal to df columns string replace. String replace. And then we replace close. And then over here, we specify with what we want to replace it with. We want to replace it with the variable, or like the ticker name. So how to do this is we can simply use a string formatter, and we select our ticker in the string formatter. So what this does is it essentially populates the curly brackets with the being iterated ticker value or name. A quick tip here is that you can use local variable names as well. This way, if you are using multiple variables to populate your string, you do not have to take into account the sequence of variables between the parentheses of the string formatter. You can, for instance, specify x over here and say that x is equal to ticker. And then include another string you'd like to format in, and then you can, I don't know, specify another variable over here as well. So what we're having over here now is that it will essentially replace the close column name with the ticker name plus the end date as well. But we're not really interested in that, so we're going to delete the last one. Okay. When running the code now, each iteration will essentially overwrite the latest one. Therefore, we have to assure that the data is being saved somewhere. To do so, we could say if the earlier defined price data frame is empty, which it initially will be, we equate it to the data frame. So if price empty, then price is equal to df. And of course, we're referring to this data frame right now. So this data frame we're going to populate with the data from this for loop. And to do so, we first have to check whether it's empty. And if it's empty, then we equate it to, the first iterated data frame, essentially. After the first iteration of the earlier defined for loop, the price data frame will not be empty anymore, of course. It will now be equal to the data frame of our first ticker in the list, which is GUFT. Therefore, we get an else function. If the price data frame is not empty, we simply outer join the new ticker data with the existing price data. So what we get is price is equal to price join df, and how, let's say, is outer. These steps essentially make sure that the individual series will be lumped together in our previously defined empty price data frame. We conduct an outer join because an outer join returns all the rows from the price data frame as well as all the rows from being added data frame. It matches up rows where possible with not a numbers elsewhere. In other words, we simply add a new column to the existing price data frame without taking into account the existing time index. Let's check how this looks for now. So we print price. Okay, this looks about right. There's no value for CG in the first period, but it pops up later on. Okay, that looks good. To get rid of the not a numbers, we can simply drop them. So we say drop price drop NA, how is equal to any. And then we specify that in place is equal to true. And this last condition is very important to make sure that the effect is permanent. In other words, we assure that our earlier defined price data frame is actually affected by this line of code. If we would not specify in place is equal to true, then the not a numbers would still prevail in our data frame if we would call it again. Okay, so now to obtain the returns, we have to apply a function to every column of the data frame. The basic function of continuously compounded returns is the natural logarithm of the price at t over the price at t minus 1. So we can essentially do this by applying a lambda function to the column, or to each and every column. Note, a lambda function is an anonymous function. These are functions which we only tend to use once and are therefore not explicitly defined, for instance, our returns function, which is explicitly defined, this function over here. Using a lambda function, we can divide all the prices of the original column, so for instance, GOFT column, by its respective value 1 unit of time in the past. This is done by simply dividing a column by the same column shifted down by 1 unit. That is, we currently have print price head, and we want to divide it by shifted by 1 unit. So this is what we currently have. Well, this is only the top rows, of course, but you get the point. This is what we currently have, and we want to divide every column by the respective values over here. Well, we can simply do that by the apply function. This function requires an input of a lambda function as well as an axis along which the function is applied. So we say returns is equal to price apply lambda x, and then we say numpy log to take the natural logarithm of each value in the array or in the series, and then we say x over x shift 1. And now an important thing here is to specify the x's. In this case, the default axis of 0 is okay, but in other cases you might use the axis is equal to 1 option. So if we equate the x's input to 1, the function is applied to each row, and if we equate the input to 0, the function is applied to each column, and that's of course what we're looking for in this case. So by applying this function, we essentially divide all the values in the original column by its respective value 1 unit of time in the past. Thereafter, we take the natural logarithm of the division to obtain the daily returns. Again, before showing you the returns, I'll drop the not a numbers, as the return calculation generated not a numbers in the first row. So we say returns, drop na, and then how is any, and in place is equal to true. Let's print the returns and see what we got. This looks about right. Great. So now one final step is to, well, export the data to a CSV file. We can do so by saying returns to CSV, and let's call this file returns.csv, and then we can run it and we're done. Well, that's about it for this video. Next video we'll dive into the efficient frontier. So we'll start using the data, we'll start using the returns data, and well, essentially get some analytic insights from that. Hope to see you next video.